It's my pleasure to welcome you to the 2021 Allen Distinguished Lecture. The reason is that you all understand that we were unable to have the lecture in person last year, but we kept in contact with our distinguished lecturer. So I'm very pleased to welcome Dr. Recording Tromp from IBM Yorktown Heights, who is officially our 2021 Distinguished Cowley Lecturer. I'd like to start by giving you a little bit of background to the Cowley Lectureship. John Cowley came here in 1970, and he rapidly established what became a leading school, internationally famous for high-resolution electron microscopy developments and applications. And he attracted a number of faculty in the field of electron microscopy into a physics department, which is quite anomalous in this country. But over the years, we grew and we prospered. And John Cowley, before he passed in 2003, we were able to rename our microscope facility the John Cowley Center for High Resolution Microscopy. John passed away in 2004, and in 2005, we were able to raise sufficient funds to establish the Cowley Endowment, which enables us to invite one per year. So we've had two recently, but that's okay, you understand the reasons. We are able to bring a distinguished international expert in the general area of microscopy, imaging, or diffraction to come to ASU. So Recording Tromp accepted our invitation. We're delighted. Ruud did his bachelor's degree at Twente University in the Netherlands, PhD at Utrecht, and maybe you'll let me tell you the time. It was way back in 1982, but he was only 5 years old at the time, so he was a child prodigy. So don't try to work out how old he is, okay? Anyway, Ruud in 1983 went to Yorktown Heights, and he's done all sorts of wonderful things in the general area of surface science, epitaxial growth. He was a major leader in developing the lean, which is now a technique or an instrument that is worldwide in many laboratories. So Ruud has accomplished many scientific firsts over his career. He's been highly distinguished by many awards, including the Davison-Germer Award from the American Physical Society. And just a little part of pride here, he was also the Distinguished Physical Scientist of the Electron Microscopy Society of America this year. He's received a number of awards. He's a member of the National Academy of Engineering, and he's part of many societies. And so we are delighted to have Recording Tromp here to give our Cowley Distinguished Lecture.
Thank you. Can you all hear? Yes, you can all hear me. So thank you very much for those kind words. It is wonderful to be here. It took patience and perseverance, but in the end, here I am in front of you. This is, I don't even know, probably the 5th or 6th time or so that I stand in this space and give talks about all kinds of things. The last time I was here in 2016, I gave a talk about the history of surface science. So that was a completely different topic. And what I'm going to talk about today is sort of, well, it says in situ imaging and spectroscopy with few EV electrons. This is work that was done in part at IBM, where I've been for the last 40 years almost. And part of it done at the Kamerlingh Honors Laboratory in Leiden, where I am a part-time professor, and I will show some of the work done there. So this is John Cowley. And I was lucky enough to have met him several times when he was still working and teaching here. And unless I'm gravely mistaken, he sits here at the controls of the Midas machine, as it was called. It's certainly a VG STEM. And he was not only a wonderful experimentalist, of course, he's well known for his book on diffraction physics, which you can still buy on Amazon or any reputable bookstore. He had many, many students, and I was lucky enough to have Marion Mankosh, who was a student who actually did work on the Midas machine, doing holography on magnetic materials. He, after his PhD in 1994, he did a postdoc with me at IBM in the very early days of my developing and using low energy electron microscopy. And nowadays he works on a project which is called multi-pass electron microscopy, where the electrons go through the sample many, many times and build up phase contrast sequentially. So if you're interested in that, you can look that up. It's an interesting project. A little bit more history. A contemporary of John Cowley was just this gentleman. In the background, you see the experiment that I did during my thesis project right here. It was an ion scattering thing. This gentleman is called Jaap Kistemaker. He was the director of the institute. And the reason I bring him up here is, well, not only to show that, that I started with paper tapes and graduated to electronic devices, but also he always gave us a piece of advice, which I'd like to share with you. He said, by the time people start organizing large conferences on the topic you work on, it is time to go and do something else. And that is advice that I've tried to follow over the years. So when David says I've worked on a large number of different topics, that's why. It does two things. It makes sure that you're not competing with thousands of other people who are doing the same thing, which is never a good situation to be in. It also keeps work from getting boring, right? So change is very good. He changed the topics at this institute many times, and I think it's a good model following. I did this experiment during my, and I'm not going to explain even what this graph means, but this was one of the, I studied the silicon 100 surface. My thesis advisor was Frans Arias, who's a good friend of mine. And what we showed is that there's about one monolayer, you see here, one monolayer of atoms on the surface that is displaced laterally. Then when I came to IBM, this was in the very early days of scanning tunneling microscopy. So we looked with STM together with Bob Hamus and Joe DeMuth at this silicon 100 surface, and we saw these little jelly beans. You see these rows of jelly beans? They are dimers. And this was the first time that anybody ever seen atoms on this silicon surface and understood in real space what the structure of this surface is. Plus that there's a lot of defects in the surface, but that is not, that's typical for surfaces, right? There tend to be a fairly large number of defects. So this was, you see the date here in 1985, right up here. In that same year, Ernst Bauer, in the back of the audience here, and Wolfgang Telix published this paper in ultramicroscopy, you see also 1985, analytical reflection emission UHV surface electron microscopy, where they show that if you bounce electrons from a surface at very low energy, a few eV, and you use the reflected electrons to form an image, you can see atomic steps on the surface. And I heard Ernst give a talk probably 2 or 3 years after this, where he showed a movie of this silicon 101 surface, where at high temperature, there's a coexistence between two phases, a disordered one, what we call 1 by 1 phase. And these little triangles that come out of the atomic steps is the famous silicon 101 7 by 7 reconstruction. And there'd been a long discussion about whether this was a first order or a second order phase transition. Here you see coexistence of the two phases side by side. So there's no more question, it's a first order phase transition that stretches over some temperature range due to finite size effects. Right? And so I saw that movie and I was interested in epitextual growth. And I went back to my boss at IBM. I said, here's this professor in Germany who's built this microscope, and I want to understand how crystals grow. If I build one of these microscopes, then I can watch crystals grow rather than doing post-mortem analysis on them, right? And so the upshot of that is that I got to design my first LEAM system. This was published in 1991, a few years later. This was the second operational LEAM in the world at that time. And here's a picture from a research magazine a year later where you see there's a lot more stuff on the microscope. Actually, in this photo, it didn't work yet. A year later, it worked beautifully. And we used this microscope for a number of years and did many different types of studies with it, including crystal growth and phase transitions and whatnot. We note in the paper that this is the first electron microscope we ever built, and undoubtedly we've made some mistakes. Both of these were true. when I got into this project, I'd actually never touched an electron microscope before, and it was just pure ignorance that convinced me that I could do this, and it worked out okay. But so this was the first microscope that we built, an electron gun. We go through a 90-degree beam deflector. Marian Mankos, the student that I just showed on the slide with John Cowley, he helped me design this centerpiece here. The beam goes to a sample, and the sample sits at a potential which is almost equal to the gun potential. So if you extract 15 kilovolt electrons from the gun, then the sample sits at 15 kilovolts plus or minus a few eV, depending on exactly what experiment we do. So if the sample is slightly more positive, then the electrons actually hit the sample, reflect back, and we can use them for imaging. And then the bottom end of this microscope is basically very similar to the image forming system, the projector system of a TM column. Oops. A couple of years later, we added the second piece of optics here, a second deflection system plus an electron mirror. And the electron mirror allowed us to correct the spherical and chromatic aberrations of the objective lens. So without this piece of optics, the resolution using a cold field emitter is about 4 nanometers. And using this electron mirror, which you see is actually a very simple element. This is a ground plane. This is a high voltage plane that reflects the electrons. And then there are 2 intermediate plates that you can use as a focusing lens, right? So you have 3 elements here, 2 focusing elements in the mirror. You want to control 3 things: the spherical aberration coefficient, the chromatic aberration coefficient, and the focal length of this thing. And it turns out that you have 3 variables that you want to control. You have 3 knobs, and it turns out it's just enough. You can exactly do what you want. And that was the original experiments there were done by Gertrude Drempfer, who was a professor at Portland State University in Oregon, and Oregon State University in Portland, I should say, and Harald Rose, who helped to develop some of the theory related to this. So with this, we get a spatial resolution after 2 years of tuning of about 1.4 nanometers, right? You see 2.3 times the wavelength of the electron. The best TMs get something like 20 times the wavelength of the electron. Of course, those wavelengths are much shorter, but nonetheless, in this LEAM, where a wavelength is really quite large, in the order of a fraction of a nanometer, we get very close to what you would think is the diffraction limit, should be the diffraction limit. One of the beautiful things about LEAM, of course, is that you can do live microscopy with it, which is why I got interested in the first place. On the left here is a movie of a polycrystalline piece of nickel. So just a nickel foil that I pulled out of a drawer, and you see the grains, and I'm slowly heating up the sample now. If you look here, you see some of those grains get punched out of the film. I think it's this grain here, but she'll start shrinking. There's all kinds of changes on the surface. At high enough temperature, the oxide comes off, and we see atomic steps on the surface, right? So we just cleaned this thing up. And I hold it there. This is probably at about 800 Celsius or so. This was a real-time movie. So this piece of the whole experiment took 10 seconds to do, right? And if you wouldn't have this real-time imaging capability, you would have missed the whole thing. Then when we cool the sample down, it turns out there's a little bit of carbon dissolved inside the nickel. And the carbon comes out, and you see how it forms one monolayer of graphene on the sample, right? Just by cooling. If I heat it up again, the carbon will go back in, and so you got this totally reversible thing. And this, and you see that the film slowly closes. I'm not going to run it again, but you will see that as the graphene grows, the nickel steps run away from the graphene edge. There's a lot of physics going on here that you could spend more time on. So here's the same sample. This is the clean sample, and we're now going to measure the reflectivity of the 0th order diffracted beam. So the electrons hit the sample, they diffract, and there's a specular beam that comes back, right? So no parallel momentum transfer. And we're going to measure the intensity of that electron beam as a function of energy, the landing energy of the electrons. So we see that at about 20 eV, there's a big peak in the spectrum. We can also measure that in area A, where we have one monolayer of graphene. And we see this spectrum has really changed rather dramatically. And this small area B here, where we have two monolayers of graphene, right? And you see again, well, this is one monolayer of graphene, this is two monolayers of graphene. You see the spectra are all very different. Now you can calculate, if you put in the atomic structure, you can calculate what you expect. And so for clean nickel, looks very much like the experiment. And here we have choices. We can put the carbon atoms either on top of a nickel atom or in a hollow. It turns out they sit on top of the nickel atom. That's the comparison here. And then we have two layers of graphene. You can shift them either exactly on top of one another, right? So the two chicken meshes fit exactly on top of one another. Or you can shift them so that the second graphene atom sits on the hole of the first graphene atom. It's called AB. And it turns out that it likes to form this AB stacking, right? So we can, from this, we can determine the atomic structure of these films with a spatial nanometer, the spatial resolution, which is detected, which is determined by the spatial resolution in the image, a few nanometers. So we see atomic structure within an area of a few nanometers, right, from the diffraction. You can then also place apertures here and here and record an electron energy loss spectrum. If you do it on one monolayer, this is the elastic peak. There's not much interesting going on here. When we go to the two monolayer part, we see there's a strong pi plasmon and a sigma plus pi plasmon. You might ask, well, why don't you see that from one monolayer of graphene? That's graphene also. But that first monolayer interacts with the valence electrons and the nickel so strongly that these plasmons are completely damped. When you go to two monos, the second monolayer doesn't see the underlying nickel anymore. So you don't have that damping and you get a very strong pi plasmon. So we can also, just from looking at this electron energy loss spectrum, we can learn something about the electronic structure. It turns out we can learn much more from about the electronic structure that I will come to later. So let's look at graphene a little more. This is a set of experiments done by Tobias de Jong at Leiden University, who will receive his PhD in about 2 weeks. And he looked at a piece of graphene that was transferred using Scotch tape on a silicon oxide sample, right? And so this is an image. It's about 35 microns by 25 microns. And so these are 120 images that are acquired. And you can see sort of the shadows of these images using the computerized stage. These images are then stitched together with a stitching algorithm, much like what your cell phone does, you know, when you take a panorama shot. And so we can zoom in on this, and I'll zoom in a few times. And you see, when you zoom in, there's all this stuff that becomes visible within these small regions on the sample. More and more stuff. And what happens is that we have two monolayers of graphene here that sit on top of one another. But when they put the second layer of graphene down, they slightly rotated the sample. So these two layers of graphene are rotated relative to one another. So what you expect to see is a moire pattern between those two graphene layers, right? They're twisted. People are interested in this because when you twist it exactly 1 degree relative to one another, it forms a superconductor. Who would have thought, right? But that's in fact what happens. So people are interested, and people call this twistronics now. You're going to call it something tronics, so it's called twistronics. It's how the electronic behavior of these materials depends on twist. So now we can look at a few different areas and get images. And so here we see images at 0.08 degrees rotation, 0.18, 0.26, and 0.63. And you see those dark lines in the image, which are part of the characteristics of this moire pattern, right? And they allow you to, just from the Fourier transform, to calculate the twist angle. By the way, they found one area where the twist angle was exactly 1 degree, brought it to a synchrotron, did angle result photoemission on that, and saw that indeed the electronic structure was very peculiar under that rotation. So here we have these two layers twisted relative to one another, and there's different types of stacking. You see in the center here, those two chicken meshes lie exactly on top of one another. We'll call that AA. And then these are symmetry related, right? This is just the mirror reflection of that. We'll call that AB and BA. And if you look at the energy, it turns out that this region where the two lattices are exactly on top of one another, this is this region here, theory tells you that is energetically very costly, right? So it doesn't really want to do that. And what happens instead is that these blue and these red regions, they push out and they minimize this area in the middle where they sit exactly on top of one another. And then there are saddle points between them, right? Where it's like a partial dislocation. You go from one stacking to another stacking, right? Now we're going to take one of these areas of the sample you see here. It's not exactly regular, so we do a fine transformation so that this becomes a perfectly triangular lattice. Then you can do a unit cell average and measure the image intensity across a scan across the unit cell here. It looks like this. So you can measure the image intensity at some electron energy, right, as a function of position. When you do that along the three symmetry directions to the unit cell, you see that the intensity, the image intensity looks very similar, and they should be because they're equivalent directions. And when you compare it to theory, here you see that there's very strong correspondence between the theory and the experimental results, right? And that means I showed you when you measure the intensity as a function of energy, you can extract atomic structure, right? And that's what we do here. So we extract the atomic structure both in the AA region where they sit on top of one another with that outerlateral shift that agrees very well with the theory, and in the region here where you go from AB to BA, that's a narrow region with its own unique structure, and again we can determine the atomic structure on that. So this allows you to determine atomic structure on really small length scales that otherwise would be difficult to do using these very low energy electrons. I want to talk about dislocations a little bit, and I noticed that you have lots of those in Arizona. Dislocations are small, right? There are things with a core that is of an order of a few angstroms or so, and we don't have enough resolution to see those, but it turns out that we can use this Moiré lattice as a magnifying glass for the dislocations. So let me show that to you. Here's a dislocation, right? If you follow this line here, it ends at a twist angle of 0.28 degrees between the top and bottom layer of graphene. We can draw a Burgers. This is John Burgers, who was a professor at Delft University. We can draw a Burgers circuit. So we go 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and there's a missing piece. That's the Burgers vector, right? And you see it's big. It's this is nanometers, so this Burgers vector is about 5 nanometers on the Moiré lattice, right? How is that related to the atomic scale Burgers vector? Well, this is the bottom layer of graphene. You see a 5-fold and a 7-fold ring here. So this is the core of the dislocation. You can again do a Burgers circuit, and you find that this is the Burgers vector of this dislocation, right? We put the top layer of graphene on, rotated just for illustration purpose here by 4.5 degrees. And here in the Moiré lattice, again, you see a dislocation and you can determine the Burgers vector. Interestingly, the real space, the atomic Burgers vector and the Moiré Burgers vector are rotated by 90 degrees, right? So this Burgers vector here tells you that the dislocation, the atomic scale dislocation, is normal to it. Now, the Moiré pattern functions as a magnifier with a magnification of 1 over the rotation angle. The rotation angle is 0.28 degrees. So if you take this Burgers vector, 50 nanometers, divided by 1 over theta, so we divide by 208, you get an atomic scale Burgers vector of 0.24 nanometers. And for graphene, we expect a Burgers vector of 0.246. So this very simple method allows us to see dislocations in this bilayer structure, even though our real space resolution is not nearly enough to do it. But we have this fortunate effect that the Moiré lattice acts as a magnifier for what happens on the atomic scale. I want to move on to different forms of spectroscopy. So here we did spectroscopy by measuring reflectivities, et cetera, as a function of incident electron energy, right? But we can also use, we have this 90-degree beam deflector. So the sample is here, we have a couple of lenses, then we go through this 90-degree beam deflector. Remember, the electrons came from the gun to the sample and then to the projector column. This is a 90-degree bending angle, so there's an energy dependence of that. Fast electrons will take the outside curve, slow electrons will take the inside curve, and we get energy dispersion. So if you get electrons from the sample back and we pass them through a slit, then in the bottom side here, we see an energy spectrum. And this is a demonstration. This is just electrons bouncing back from a thin SiO2 film on silicon. And as a function of energy, we see this parabolic band appear. This is just the parabola of electrons in free space, right? So energy equals k squared. And so you have a bounding parabola. These are low energy electrons. These are the high energy electrons, and anything in between. I'll show experiments for graphene again. These were experiments by Soren Olstrup at Berkeley. He uses one of our microscopes. They come in with ultraviolet light here. The sample creates photoelectrons, right? So the photons make photoelectrons. The photoelectrons come out. We take a narrow slice out of the angular distribution and then project the thing on the screen. Here's a real space image against silicon carbide with graphene on it. You see different contrast here because you may have 1 or 2 or 3 layers of graphene on different parts of the sample, which give different image intensity. So here we have mostly bilayer graphene. Here it's mostly monolayer graphene. We can now map energy versus momentum of the electron, how far they are away from the optical axis, right? In the back focal plane. Here you see the pi band. Sigma band is down here. So this is and here are the Dirac points. So the singularities in the electronic structure of graphene. If you go to 2 monolayers of graphene, bilayer, you see that this pi band splits up. And you see that can you see that? That this little Dirac point is split up also. There are 2 bands that are just slightly offset relative to one another. Those are the 2 layers interacting with one another. You can do a little better. You can actually create the whole 3-dimensional electron energy versus momentum figure here. Now we can place a small contrast aperture just on the Dirac point, just at the singularity at the edge of the Brillouin zone, and form an electron image with just these electrons. Right? So now we select a tiny spot out of the total 3-dimensional band structure out of this material and form an image just with those electrons. So we know that this, and you can see there's bright areas and the dark areas. So you know the bright areas here, they carry these electrons. That's why we have graphene. Where we have these dark areas, which you see happen to be dark here also, we have no graphene. So it allows us to do a spectroscopic analysis of, first of all, we can study the band structure in detail, but then we can then carry that back to the image and see which pieces of these band structure appear on the sample, right? Now, photoemission is a rather complicated phenomenon. Here's an older experiment where I grew a silicon flake, a silver flake on a silicon crystal. This part of the flake is silver 111, and this part is silver 10, just by accident. This is what I found in the sample. This is imaged with secondary electrons. This is imaged with d electrons. So these are photoemission images where I selected different electron energies on the sample. Here you see the electron energy spectra. This is excited with the helium-1 light source that's attached to the microscope. So this I don't have to go to a synchrotron for, I can do it at home. And here you see the spectra. And when we take this peak here, this strong peak that we see, and plot its intensity as a function of momentum, right? Parallel momentum on the sample. You see that on 111, there are 3 strong lobes, and on this part of the sample, there are 4 strong lobes, and they're obviously rotated in a different symmetry. Why are these lobes so strong? And it turns out that's sort of a coincidence. This is the band structure. So these are the energy bands of the electrons in the solid. So these are occupied bands down here. These are unoccupied bands. Normally, we don't talk about the unoccupied bands so much. There's no electrons there, so we think, well, they don't do anything either, right? It turns out that they're quite important. So if we excite this, you see this is called the L point in the Brillouin. It's on the edge of the Brillouin zone. It turns out if we excite from this band here, which is an occupied band, up to this unoccupied state, that separation happens to be, by coincidence, exactly equal to the photon energy that we use, right? So we excite from this highly occupied state to this high density of unoccupied states, right? It's a resonant transition. So this is a very strong signal that we get here. Then once the electrons are in this unoccupied band, then they can go out in the vacuum and we can detect them. If this photon energy had been 1 eV higher, then we would have been here just under this letter A. There's no bands there, so that photon could not have been absorbed because there would have been no state here where this electron could live for a little while before it goes into the vacuum, right? So people often think that photon emission, you go from here directly into the vacuum. No, the sample doesn't know about the vacuum until the electron is actually up in the unoccupied band and can escape into the vacuum, right? So it's always this absorption from an occupied into an unoccupied state and then into the vacuum. So the question is, so we see here, we're not just sensitive to the initial state, but also to the empty states, which people usually don't talk about very much. So the question is, can we see these empty states without using photons? Is there a way of probing those? These empty states are important for a lot of optical properties, for instance, of materials, right? Well, we go back to 1972, when I was -3. And here's a calculation of a band structure by Paul Marcus and Don Jepson, who at that time were at IBM, and Franco Jonah at Stony Brook University. Here's Franco. I couldn't find photos of Paul and Don, but I knew both of them, of course, but here's Franco Jonah. Here's the band structure plotted as a function of vertical momentum. And here's the intensity of the diffracted beam, right? And what you see at this energy range here, between 10 and 15 eV or so, the theory predicted that you have a very strong diffracted beam. Basically, all the electrons come back, right? The diffracted intensity is 1. At the same time, the Bloch state inside the solid is 0. So all the electrons come back and no electrons go into the solid. Why is that? Well, it is because we have a huge band gap here. You see in this region here, there are no states in the band structure. If there's no chairs to sit on, right, you got to stand. So if there's no place for these electrons to live, they cannot enter the solid. They must come back, right? And so here we see already in 1972, by this, at that time, well, it's a relatively straightforward calculation, but you see that the reflected electron intensity in this simple case is directly related to the unoccupied band structure. All right, so how do we do this experiment? This is called ARPES, angle resolved photoelectron spectroscopy. I showed that to you. You bring a photon in, the electrons come out, and you measure the intensity of the electrons as a function of energy and as a function of momentum, right? The angle at which they come out. And that gives you the bands you can see the states that the occupied electrons live in. How do we get up here? And we call this angle resolved reflected electron spectroscopy. What we do is so this is ARPES. We bring photons in, electrons out. Here we bring electrons in, electrons out. And you see this is symmetrical. So we bring an electron in, it strikes the sample at some energy, at some parallel momentum. That beam will diffract and come out again with the same energy and the same momentum. So energy and momentum are conserved. And the relation between the incident wave and the exit wave is the reflectivity, right? If all electrons come back, reflectivity is 1. If all the electrons go into the solid, nothing comes back and reflectivity is 0, and everything in between. So now that's a pretty simple experiment to do, because you can just bring the electron in at some angle and measure its reflected amplitude. How many come back? So we do that. And I'm going to show you again a graphene sample. This is graphene on silicon carbide. And we're at normal incidence, and we're going to measure the reflectivity on different places. You see the different places have different colors. And you see that we get different reflectivities, right? So in position blue up here, we have 1 minimum here. And in position red, we have 2 minima. And in position green, we have 3 minima, etc. And it turns out, and I will explain to you in a few minutes why that is, that the number of minima here corresponds to the number of graphene layers that sit on top of one another. You can think of it this way. If I have two layers of graphene, we can have a state that lives just between those two layers. And this minimum occurs just at the energy of that state. So now we have a state, the electrons can go in there. And so the reflectivity is very small. If I put two layers, if I add a layer, then I have a state between the first layer and the second layer and the third layer. They interact with each other and they split, right? They lift the degeneracy. So now I get two of these minima, etc. So you can count how many layers have from this. And that's shown here. So here's the same curve. You see we have three layers of graphene, two minima, and plotted here as a function of energy at normal incidence. So K parallel is 0. If you now tilt the beam to measure that as a function of incident angle, then we find that these states are not at constant energy, they disperse, right? And if you look at this dispersion, so this is K parallel, the in-plane momentum of the electron. And this is the energy. It turns out that this curvature corresponds to the mass of the electron being about 1 electron mass, very close, almost 3 electrons. Then we see a large red area. Red means high reflectivity, which means that we have a big band gap here. The electrons cannot go into the solid there. And then at higher energy, we see different bands develop. And it's known that graphite, for instance, does have a big band gap about 10 eV above the vacuum level. So here's the same thing on boron nitride. You see a very different pattern. Here's a first principle simulation. We see a strongly occupied state here. Blue means low reflectivity. We see that in the experiment. A big band gap in the middle here, which you see in the experiment also. You see these side bands here and here that occur in the experiment. And if you just plot the band structure on top of that, you indeed see a large band gap in the band structure here. You see these side bands appear and everything. So this simple reflectivity experiment actually shows you the band structure of the material rather directly. And we can actually do that in 3 dimensions. So here are slices with, this is just in one direction, but we can do kx, ky, and get the whole 3-dimensional figure, right? So you see here at 10 eV, if you look at the band structure as a function of the in-plane momentum, it's very highly non-uniform, right? And it's got the 6-fold symmetry. You see here, it gets to a 3-fold symmetry, etc. And here are simulations that show similar effects. Here is graphite hexagonal boron nitride reflected electrons, and in the same microscope on the same sample, we can do angle resolved photoemission and look at the unoccupied bands. The little piece that we miss here, about 5 eV, is between the top of the valence band and the vacuum level. There's a region that we can't access experimentally. And here's a similar series for different metal dichalcogenides. For instance, here you see a very pronounced state inside the band gap in theory, which we also find in the experiment. And then you see these strong parabolic bands up here, both in theory and experiment. You can see them in the spaghetti plot here, these strong parabolic bands. You have direct access to the unoccupied bands in the material. This is interesting because nobody's done this before. There's like tens of thousands of papers on angle resolved photoemission, but nobody's been able to look at these unoccupied states before. And here for the first time, we really get a very detailed look at them. All right. So here we've looked so far at electrons that we aim at the sample. They reflect from the sample, they come back. So we look at reflectivity. What I'm going to talk about next is what we call transmission lead, electron volt transmission electron microscopy. Most of you here, many of you do transmission electron microscopy. You use microscopes that use energies of 100, 200, 300 kilovolt, right? The electrons go through the sample and you look at what comes out. What we're going to do here is use electrons with just a few EV energy, few electron volt, right? You might wonder, can you see anything? Well, here's a plot of the mean free path of electrons This is called the universal curve. I'll tell you right now that it's wrong, but it shows that below 10 eV or so, the electrons can travel deeper into the solid again, right? Why? Because there's nothing left to excite anymore, basically, right? You cannot excite plasmons anymore. There's not enough energy. So these electrons can't lose their energy, so they gotta keep going, right? It's a car without brakes. That's the idea. And so what we do in the experiment is here we have our normal electron gun. We can look at reflection, but we can also mount a miniature electron gun behind the sample and shoot the electrons from this side. Then they come out the front, and we image again with the same electron optics, right? So we can measure reflection coefficient as a function of energy and transmission coefficients as a function of energy. This works. This is one of the first images we took on graphene, multi-layer graphene on holy carbon. You can see the holy carbon framework here. So this showed us, yes, we can do this experiment. The electrons come through, right? So now we can start doing spectroscopy with those. Here's an image of this is a TM grid. There's a 2 micrometer hole in it. Here we have graphene. This is in reflection. And here we see the same area in transmission, right? Reflection. So we switch from one electron gun to the other, back and forth, and we get these images. I showed you these curves before, right? So if you look at reflection, we have 1 minimum or 2, depending on how many graphene layers we have. And I promised you I was going to explain how that works. So let's just focus on the top left here. We have 1 layer of graphene. We have a plane wave coming in. We have a reflected plane wave. We have a wave coming out. And in principle, we would also have a plane coming from the right, but you know, that thing is 0 because nothing reflecting it here. So we have reflectivity R, reflected amplitude R, and transmission amplitude T. Now, if we add a second layer here, we have waves coming from the left. They're either transmitted or reflected. There's a second layer here. And so when the electrons travel from the first to the second layer, there's a phase accumulation, right? The electrons got to cover some path length and will acquire phase. So that's given by this phase vector phi. And then the same game happens. They can either reflect or transmit. And you know, if they reflect, they can come back here, they come back out, or they can reflect here and go back, right? So you get an infinite sum of terms. You get an infinite sum of terms. And then if you have n layers here, then you just put brackets around this and you say, okay, we do that to the power n or n minus 1, right? So you can think of this as matrix multiplication effects. You can work out these sums easily. This was done by Lord Rayleigh for the first time in 1917. Just classical optics. That's what I'm doing, right? This is classical optics, multi-layer optics. And you get the transmission and reflection amplitudes. And amazingly, there's no quantum mechanics in here. This is just, we have reflection, transmission amplitudes, and we have phase accumulation, right? Amazingly, if you use this formalism and calculate what these curves look like, they look like this. This is experiment, this is theory. Right? The only thing we've done is that as the energy increases here, you can see that for the 1 layer case, the reflection is constant up to the plasma energy and then slowly decays, right? And that way we can reproduce these experimental results with this very simple classical optical theory. So if we put an arrow here where the reflectivity is very small, this is an anti-reflective coating for electrons. Just like you have an anti-reflective coating on your glasses. Exactly the same. Right? Now we can do this both in reflection and transmission. So this is reflection, this is transmission. And you see where the reflection is small, the transmission is high. The car has no brakes. It just keeps on going. It finds a state that it can live in and it will just travel through. And you see when the reflection gets high again, because now this anti-reflective coating doesn't work anymore, then the transmission goes down, right? So we have 2 measurements. We have, and these are absolute numbers. We have, in this case, a transmission of 0.55 or so, a reflection of 0.15, and so there's a little bit missing. That's the inelastic piece, right? You have the two elastic channels, and whatever does not add up to one, that's the inelastic channel. So we have the inelastic channel, we have both the elastic channels. We can now, did I go right? Yeah. We can now extract the mean free path. There's the total mean free path, how far the electron can travel at a given energy. And what is interesting, this is for one layer. When the layer gets thicker, it can actually travel faster, further. You see 2, 3 layers are longer mean free path than one layer. Why? Because we've created this highway for the electrons to travel on at that energy. The inelastic mean free path is just 2 or 3 layers, right? Very different from what this universal curve promised us. The universal curve promised us we can travel, hundreds of angstroms. No. This is the elastic mean free path. And look what happens. The elastic channel goes up to 80 angstrom, to 80 layers, right? This is this state, this highway for the electrons to travel in. And unless they get scattered inelastically, they can just keep on going forever. This again is for this bottom curve. This is our toy model without energy losses. This is with energy losses built in, and you see, and this is a full quantum mechanical theory, band structure theory with the scattering built in. And you see this very simple, stupid toy model actually explains everything that you see in the experiment, right? We can do this for molybdenum sulfide. I will just show to the elastic mean free path, very small, 1/10 of a layer, right? The electrons simply do not want to enter the solid. Why is that? We can look at our angle resolved reflectivity. What we see is this huge band gap here, right? We have this huge band gap which corresponds to the electrons not being able to enter the solid. What's more, it's very strongly angle dependent. So if you look here at 5.6 eV, you see, there's very strong angular variation. So not only is the mean free path dependent on energy, it's also dependent on momentum, because different momenta have different band structures, different bands in different places. So what do we learn from this? It really gives us a new way to look at both unoccupied and occupied band structure, look at mean free paths. You see the empty states, energy and momentum resolved, allows us to obtain these elastic and inelastic mean free paths. The electrons cannot exist at the energy and momentum where there's a band gap. That should be no new news, right? If there's no state for the electron to be there, it cannot be there. Yet in all the analysis that I see on angle resolved photon emission data, where you always go from an occupied state to an unoccupied state, that is just always left out of the story. They always pretend like it goes directly into a vacuum-free electron state. That's not true. The last 2 years, I've worked on building, so here's the electron gun is a cold field emission gun, which has a width, depending on where you measure it, of a quarter EV to an EV or so. I'll show it in a second. And we could do better by putting an energy filter in the gun. So here's the gun. We shoot the electrons. We go through a 90-degree deflector, which disperses the electrons, right? So in this plane, fast electrons are on this side, slow electrons are on this side. If I put a narrow slit in the middle, I can just pick out a little band and get much better energy resolution. We then go to the sample, we undo the dispersion here, and the rest of the experiment works the same. It required a lot of new optics, but so why would you want to do that? So this is the energy distribution of a lab 6 emitter. It's a broad Gaussian, width of about a 3/4 to an EV or so. He's a cold field emitter, full width half max about 0.25 to 0.35 EV. And we can just pick out this narrow band using the energy filter. So first we make the energy distribution Gaussian, right, symmetrical, and we can make it much narrower. Here's this filter slit. Actually, these slits are only a micron wide, and there's a second set where they're only half a micrometer wide, very narrow. We focus the beam and tease it through this little slit. Here, the beam is defocused on this energy selection slit, and so we can draw a trace through here, and we see the energy distribution of the gun. You see it's about, in this case, 0.35 EV wide or so, and has a very long tail, very typical cold field emission electron distribution. When we focus the beam, rather than a broad beam, we focus it on the slit here, then we have the slow electrons here, the high energy electrons here, and we just take this little slice out of it, right? So we get much better energy resolution. Now, why is that important? Let's first see. So here I do an experiment which you call a mirror to Lehm experiment. So initially, the sample potential is more negative than the electron gun. So the electrons come to the sample, they slow down, and then they find that the electron is more negative, the sample is more negative than the electrons are fast, right? So they turn around in front of the sample, they never touch the sample. Then when I slowly make the sample potential more positive, the electrons come closer and closer. At some point, they hit the sample. And when they hit the sample, the reflectivity changes from 1 to something smaller than 1. So without energy filtering, just we see this happening here. So the reflectivity is 1 here, and then it drops over about an EV or so, because this energy distribution is very broad. When I turn the energy filter on, which means I put the slit in, this becomes symmetric and it becomes much narrower. So it's about 130 millivolts wide here. There are 2 different regions on the sample here, white and black, and they're shifted relative to one another by, in this case, 70 millivolts or so. Here we do it again. This is a silicon 1-on-1 surface at high temperature. The black triangles are 7 by 7. I've showed this before. The dark circles are 1 by 1, and we measure a shift in this potential, which means there's a shift, a difference in work function. The electrostatic potential in these 2 phases on the sample is different, in this case by 70 millivolt. By here, what did I say, 130 millivolt, right? So these are 2 different structures, 2 different atomic structures, and they have a different electrostatic potential associated with them, which we measure here. Again, and we can measure that on areas as small as 10 nanometers or something. So you see that this experiment went from a very sluggish, poorly resolved broad distribution, something that's much narrower. When I changed the energy filter slit from 1 micrometer to 1 micrometer, I can make this even sharper. You see this fit here is an error function. There's the Gaussian energy distribution on the gun, and we get a full width half max of about 100 millivolts. Now, why is this important? Typically, we measure this electrostatic potential by measuring this transition from mirror mode reflectivity 1. And this again is on, you recognize this now, is on 3 layers graphene. And we say, well, the electrostatic potential is sort of given by the midpoint here, right? So we draw the midpoint and say, okay, it corresponds to what I called 0 EV here. This is unfiltered electrons. When I filter the electrons, you see the minima get deeper, etc. But more importantly, we see that there's actually a shoulder here, which in the blue data you can very weakly see, right? So we find that the half point is actually not here, but it is here. It is where we drop down to this plateau. And the shift is quite significant. It's 400 millivolt, which if you're interested in what the electrostatic potential is, if you think of chemical terms, it's a huge difference. The electrochemical potential differs by 400 millivolt between those 2 measurements. You can also think about spatial resolution. So if you look up this book that Ernst wrote, Surface Microscopy with Low Energy Electrons, and wonder, well, if we turn the electrons around just in front of the sample, we never touch, right? But we can still see stuff on the sample. If the sample is rough, we'll see that. And in his book, Ernst writes, well, the spatial resolution is in the order of 80 nanometer, in good agreement with the best experimental results. And further on, he says the lateral resolution of mirror microscopy is not significantly better than 100 nanometers. And that's kind of strange because, 5 minutes, is that about that? Yeah. If I look at the aberration coefficients, and these were worked out by Gertrude Drempfer a long time ago, in mirror mode, they're given, so this is the chromatic and the spherical aberration coefficient, 2 times L, where L is the distance between the sample and the objective lens, 1.5 millimeters. So the aberration coefficients are 3 millimeters. In Lehm, they're more like 10 centimeters. Yet in Lehm, we can get a few nanometer resolution without any problem. And with these much better aberration coefficients in mirror mode, we can only get 100 nanometers. Why is that? Right? It looks like the imaging system is far better. Yes, the resolution is worse by more than an order of magnitude. Well, it turns out that let's take a sample and let's put a line object on it, right? And let's turn the electrons around at minus 100 millivolts, which means 10 nanometers away from the actual sample, right? So then the equipotential contour due to this line defect looks like this little half circle, right? If you turn around further away, so we make the electrons approach not as closely, you see that circle gets fatter and fatter. So if instead of 100 millivolt away, we turn around 1000 millivolt, then the object has become much fatter, right? The thing is, you don't actually image this object itself. You image the fields that the object creates in the vacuum, right? And they get bigger and bigger the further and further away you go. So the resolution is bad because we have always used bad electron guns, right? And if you use a better electron gun, you can get much better spatial resolution. So I'll show two examples. This is a sample I got from Caroline Ross, Francis's sister, and her student, Runza Leo. This is an AFM image that I took of this diblock copolymer sample. You see typical spacings here of 40 nanometers, much smaller than 100 nanometers that and you can easily resolve those in a mirror microscopy image also. So here, this is energy filtered. The electrons turn around about 10 nanometer away from the sample and come back, and we form an image with them. And we can image the modulation of the potential energy in front of the sample. The electrons never touch the sample, right? Here's carbon nanotubes on silicon. Here's a single carbon nanotube. Again, we are about 10 nanometers away from the sample, and the full width half max is 12 nanometers, right? Of course, the carbon nanotube is even thinner. It's only like a nanometer thick or something, but we see the width of the potential contour 10 nanometers away. Here's some more experiments, 12 nanometers, 14 nanometers, very, very similar. When we do this experiment, so here we have a trench in a sample, and these are the equipotential contours that I calculate in front of the sample. Remember, there's always a strong field between the sample and the objective lines, right? 10 kilovolts per centimeter. And here you see these equipotential contours. This is an experiment that Alfred Bock did in Delft in 1968, using an analog computer because there were no digital computers at the time, not smart enough, not powerful enough to do a ray tracing calculation. He used the cosine potential. And you see, if you come in exactly along this symmetry line, of course, the electron just comes right back because the derivative, the in-plane component is 0 here. But when you go to the edge, then the electron feels this field gradient in the horizontal direction here and is deflected sideways. So the electron undergoes a deflection angle, right? Of course, that's symmetric. That's an experiment we can do. Instead of just a single trench, we take a silicon grating. And if we form an image with the electrons turning around, say 2/10 of an eV away from the sample, 20 nanometers, and we go in an under focus condition, we see these bright lines, which correspond to the trenches here, right? Now, what if this is just with uniform illumination, right? Broad beam illumination, like you would do in TEM. What would happen if instead we would illuminate through a slit that looks like this? Right, so everything outside of the slit is blocked. We just illuminate electrons through the slit. So we just put a slit in a beam. And what we see is that as we approach very closely, the returned image, and I just keep the background image lit up, you know, for reference, so you can see what it is. You see that the electrons now get deflected very strongly. We know exactly where they came in because we know the position along the slit, right? But we see this very strong deflection, which is just this deflection that Alfred Bock calculated in 1968. And if we change the distance by which we turn around, so how close, when we turn around far away from the sample, this is a straight line, because this field has damped out, it drops off exponentially. But when we get closer and closer, we see this cosine-like amplitude forming along the illumination slit. And finally, when we hit the sample, the contrast disappears. Right? What we probe is the electric field strength outside the sample in vacuum as a function of approach distance. Filtered and unfiltered. You see in the unfiltered, it's all smeared out. Here you see this cosine fit. The potential has a cosine shape when you're far away, when you're a few tenths of a volt away. And we can, so here is this thing projected as a function of energy and location. You see the fields fall off exponentially, and that corresponds pretty well with the spacing of the grading that we're using. You can also do this in diffraction. We can look in real space. We can also look in diffraction. The angles are deflected, so in diffraction space, the angular distribution broadens in the direction perpendicular to the grading. Here you see this exponential increase of the width, and we find from that that it should decay with a decay length of 80 nanometers. We may measure 81 nanometers. Good, Maxwell's laws work, right? But so the point is, we can, in these experiments, when I just go back, if you look in these experiments here, I just take a line trace up and plot it here. So here, the top position shows where the electron comes in. As we go down, we see how the electrons get deflected depending on which position they come in. So we actually directly see the ray traces that Alfred Bock calculated back in 1968, right? We don't just get an image, we can actually follow the path of the individual electrons through this piece of optics. All right, I think that's the last thing I wanted to say. I just skipped over the thing. We added elemental analysis using EDS detectors. We have high spatial resolution, high spectroscopic resolution, electron energy loss spectroscopy. You can look at filled bands using angle dissolved photoemission inside the electron microscope, right, in the lean. You can look at unoccupied states by using this new reflected electron spectroscopy for the empty bands. Lean gives us atomic structure analysis. That's nothing new. We can do is in transmission and reflection and learn something about energy loss processes and mean free paths. With these new imaging modes that I just finished up here, we can actually do the ray tracing experiment, right? We can see where the electron path goes as a function of energy and location. And we're working on adding scanning electron microscopy to this. I got to thank a whole bunch of people. At IBM, Jim Hannon, Art Ellison, and Mark Reuter, those two people here were engineers who worked with me over many years. Rishi, Eli, and Soren Olstrup at Berkeley. Rishi helped me with parts of the design of the aberration corrector. And then a whole group of people at Leiden University that did much of the graphene work that I showed. And finally at Specs, who sells these microscopes nowadays, there's people working on continuing development. And finally, I should thank the three elders in the field, Gertrude Drempfer, who first showed that you can use an electron mirror to do aberration correction. For those of you who use aberration correctors here, right, you have this multipole optics, and there's like 80 coils that you got to balance and adjust, etc. 80 power supplies. Here, with three elements, you can not only do CS, but you can also do CC with a very simple piece of optics. So that's pretty nice. Harald Rosa, who worked out more of the theory, and of course Ernst Bauer, who started this whole field long before I was even born, and that's for real now, right? So thank you very much for your attention.